There is a hole in the universe, 700 million light-years away. A region 330 million light-years across contains almost nothing. Scientists expected to find roughly 2,000 galaxies there. They found 60. The rest are gone. Where they went, nobody fully knows. We are going to travel toward it, watching galaxies disappear, learning what emptiness actually means, and confronting the strangest fact in all of cosmology. If you enjoy the journey, subscribe and leave a like. The void is waiting. We begin now. Robert Kirshner was not looking for nothing. In 1981, he and his team at the University of Michigan were doing something that had never been done before at that scale. They were building a three-dimensional map of the universe. Not a painting, not a guess. A real map, built from measurements, one galaxy at a time. The tool they used was redshift. Every galaxy in the universe is moving away from us because space itself is stretching. As a galaxy moves away, the light it sends us gets stretched too, shifting toward the red end of the spectrum. The faster a galaxy retreats, the more its light shifts. Measure that shift, and you know the galaxy's speed. Know the speed, and you can calculate the distance. Do that for thousands of galaxies, and a three-dimensional picture of the cosmos starts to take shape. Kirshner's team had been doing exactly that. Night after night, telescope after telescope, they logged redshifts and plotted points on their growing map. Clusters of galaxies appeared. Long strings of galaxies connecting those clusters appeared. The universe looked busy, textured, alive with structure. Then they hit a wall, except the wall was the opposite of a wall. In the direction of a constellation called Boötes, the map went blank. A region 700 million light-years from Earth showed almost no galaxies at all. The team looked again. Still blank. They checked their instruments. The instruments were fine. They checked their data. The data was clean. The emptiness was real. In a universe where galaxies should be spread like sand on a beach, this patch looked like someone had lifted a portion of the beach and dumped it somewhere else. The numbers were brutal. Standard physics said that region should hold roughly 2,000 galaxies of detectable brightness. Kirshner's team found a handful. The gap was so extreme that one researcher reportedly said it looked like God had taken an eraser to that corner of the sky. Scientists named it the Boötes void. Some called it the Great Nothing. And the moment that name spread through the astronomy community, a quiet alarm went off. Because the size of the void was a problem, a serious one. At that time, the best models scientists had for how the universe organizes itself predicted some empty regions between clusters of galaxies. Voids were expected, but the expected voids were supposed to be small, maybe 30 million light-years across, maybe 50. The Boötes void was 330 million light-years wide. That is roughly the same as lining up 3 million Milky Way galaxies end to end. By the standards of every model, on every chalkboard in every university at the time, a void that big should not exist. Papers were written. Arguments broke out. Some astronomers suggested the survey was flawed. Others suggested the models were flawed. A few quietly wondered whether something else was happening out there. Something that standard physics had never accounted for. Kirshner himself was careful. He trusted the data. He also trusted that the data was going to force a reckoning. He was right about both. The Boötes void did not go away under scrutiny. Every follow-up survey confirmed it. Every new telescope that pointed in that direction found the same terrifying emptiness. The blank patch on the map was real, enormous, and stubbornly present, and astronomers had to figure out how something that big got there. The answer would take decades to piece together. And the deeper they looked, the stranger the story became. Because the Boötes void did not just challenge the models of the time. It exposed something fundamental about how the universe is built. Something that, once you see it, changes how you look at the night sky forever. To understand what carved that hole in space, you first need to understand the tool that found it. And that tool had a secret hiding inside its own method. Measuring the universe sounds impossible. And for most of human history, it was. You can see a star. You can draw it on a map of the sky, but the sky is flat. Every star looks like a dot on the same surface, whether it is 10 light years away or 10 billion. For centuries, astronomers had a beautiful two-dimensional picture of the cosmos, with absolutely no idea what the depth looked like. That changed with redshift. Here is the simple version. Light travels in waves. When something moves away from you, those waves stretch out. The sound version of this is something you already know. When a car passes you on the street and drives away, the engine sound drops in pitch. The sound waves are stretching. Light does the same thing. When a galaxy moves away from us, its light waves stretch toward the red end of the spectrum. Scientists measure how far that shift goes, and that tells them the speed the galaxy is retreating. In an expanding universe, speed equals distance. So redshift becomes a ruler. The deeper a galaxy sits in the universe, the faster it moves away, and the more its light shifts to red. Measure thousands of those shifts, convert them to distances, plot the results in 3 dimensions, and you have a map. Robert Kirshner's team was building exactly that kind of map when they found the Boötes void. But what made the discovery possible was not just the concept of redshift, it was the sheer scale of their survey. Earlier, redshift surveys had mapped small patches of sky and found filaments and clusters. The universe looked lumpy, structured, interesting, but those early surveys were like looking at 1 square foot of a city from above and concluding the whole city looks the same. Kirshner's team looked at a much larger patch, and when they did, something came into view that smaller surveys had completely missed. The void was too big to appear in a narrow slice of sky. You needed to step back far enough to see it, the way you need to step back from a building to see its shape. That scale is part of what made the Boötes void so unsettling. The void had always been there. Galaxies had been forming and dying inside its borders for billions of years. Humans had been looking at that region of sky for centuries. But the hole was so enormous that no telescope pointed at a small piece of it would notice anything missing. You needed the full picture to see the absence, and once you had the full picture, you could not unsee it. The survey technique Kirshner's team used became a foundation for everything that followed. Redshift surveys grew larger and larger over the following decades. The Sloan Digital Sky Survey eventually mapped hundreds of millions of galaxies, building the most detailed 3-dimensional atlas of the cosmos ever assembled. Every one of those surveys confirmed and refined the same picture. The universe is not smooth. It is structured like a foam, and inside that foam, the Boötes void is one of the biggest bubbles ever found. But here is what the survey could not answer on its own. A map tells you where things are. It does not tell you why. The redshift data showed the hole existed. It said nothing about how it got there. For that, scientists needed to go further back, way further, all the way back to the first moments after the Big Bang, when the seeds of every void, filament, and galaxy cluster were planted in the fabric of space itself. And what planted those seeds was something almost impossibly small. For most of human history, the universe looked perfectly fine. Stars were scattered across the sky. Some were brighter, some dimmer. Astronomers mapped their positions and drew constellations. The sky looked random, but random in a comfortable, manageable way. No one suspected there was a pattern hiding at a scale too large for any single observer to see. Then telescopes got better. Astronomers realized that many of the faint smudges in the sky were not clouds of gas inside our galaxy. They were entire galaxies, each containing hundreds of billions of stars, sitting millions of light years away. The universe was suddenly much larger than anyone had imagined, and still, for a while, it looked normal. Galaxies seemed spread around in no particular arrangement. Some areas had more, some had fewer. Randomness, astronomers assumed at every scale. That assumption cracked in the 1970s, as redshift surveys began pulling galaxies into 3 dimensions. The random scatter started to look less random. Galaxies were clustering. They were stringing together along filaments. They were grouping into massive sheets. And between those sheets and filaments were gaps, emptier regions, voids. The universe was not random, it had architecture. The first surveys were small enough that this architecture looked manageable. A few voids, a few filaments, a network of structure that seemed like it fit within what physicists expected. The largest voids spotted were a few tens of millions of light-years across. Unusual, but not alarming. Kirshner's team changed all of that in 1981. When they unveiled the Boötes void, the reaction in the scientific community was not celebration. It was closer to confusion mixed with concern. The hole was more than 10 times larger than the biggest voids the existing models predicted should form. A structure that size, under the physics that everyone trusted, should take longer than the age of the universe to develop. So either the universe was older than the models said, or the models were missing something, or the data was wrong. Scientists spent years testing all three options. The data held up, the age estimates held up. That left the models. And here is the unsettling part. The models were based on careful, well-tested physics. They described how gravity pulls matter together, how matter clusters over time, how empty regions form as matter drains away. Those processes were real and confirmed by everything else astronomers observed. The problem was that no version of those processes seemed fast enough or powerful enough to hollow out a region the size of the Boötes void in the time available. For a decade, the Boötes void sat in the literature like an open wound. It was confirmed, documented, and unexplained. Some astronomers quietly started asking whether the standard picture of the universe was missing a major ingredient. They were right, it was. But the missing ingredient would take until the late 1990s to identify, and it turned out to be the strangest force ever detected in the history of science. Before that discovery, though, something else happened. Computers got powerful enough to simulate the universe from scratch, and when scientists ran those simulations, they saw something in the results that nobody expected. The simulations grew voids, enormous ones, and the shapes those simulated voids took looked very familiar. 330 million light-years. That number sounds abstract. It is supposed to. The human brain did not evolve to handle distances like that, so here is a way to feel it instead. The Milky Way, our entire galaxy, is about 100,000 light-years across. If you shrunk the Milky Way down to the size of a single grain of sand, the Boötes void, at the same scale, would be a sphere roughly 1.5 miles wide. Inside that 1.5 mile sphere, you would find about 60 grains of sand. The rest of the space, every cubic inch of it, would be empty. That is the Boötes void. Its center sits about 700 million light-years from Earth. Light leaving there right now will not reach us for 700 million years. At that distance, the universe was already billions of years old when that light departed. The galaxies we see at that distance are ghosts of what those galaxies look like today. The void itself spans about 2% of the entire diameter of the observable universe. 2% sounds small until you realize the observable universe is 93 billion light-years across. 2% of that is a structure so large it reshapes how astronomers think about the word structure. For most of history, the biggest things in the universe were galaxy clusters. Then came superclusters. Then came the filaments connecting superclusters. The Boötes void belongs to a category above all of those. Scientists call it a supervoid. And supervoids are different from regular voids in more than just size. A regular void is a quiet neighborhood between galaxy clusters. Matter is sparse, galaxies are fewer, but the region is threaded through by faint filaments and scattered galaxies. Walk across a typical void and you would still pass the occasional galaxy every few million light-years. Walk across the Boötes void and you would pass almost nothing for hundreds of millions of light-years. The emptiness is not just sparse, it is staggering. Here is another way to feel it. If you could travel at the speed of light, crossing the Boötes void from one edge to the other would take 330 million years. During that journey, you would pass through a region where the nearest galaxy at any given moment might be tens of millions of light-years away. In the densest parts of the universe, galaxies crowd together just millions of light years apart. Inside the void, the loneliness is on a completely different level, and yet the void is not empty in the most absolute sense. 60 galaxies live inside it. Scientists have confirmed their positions. They are real, they are there, and they are not scattered randomly through the void's enormous volume. They are arranged in a shape, a pattern, a clue. That clue is one of the most important pieces of evidence scientists have for understanding how the void formed, and the shape those 60 galaxies trace is something you would not expect. It looks like a tube, not a cluster, not a random scatter, not a shell along the edge of the void, a tube running roughly through the center of the void's volume, as if a single thread of the cosmic web got left behind when everything else drained away. That shape has a story behind it, and the story starts with a collision. Imagine a warehouse the size of a continent. Inside, you find 60 candles scattered across the floor. But they are not scattered randomly. They form a rough line, a corridor running from one side of the warehouse to the other. Everything else in the warehouse is darkness. That is what the inside of the Boötes void looks like on a galaxy map. The 60 or so confirmed galaxies inside the void do not fill its enormous volume. They cluster along a tube-like structure cutting through the void's interior. Scientists spotted this pattern when they refined the galaxy sensors inside the void in the early 2000s. The more carefully they mapped the positions of those 60 galaxies, the more clearly the tube emerged. That shape is not random, it is a fingerprint. When astronomers look at the cosmic web, the structure that organizes all matter on the largest scales, they see a consistent pattern. Matter concentrates along filaments and sheets. Where filaments cross, galaxy clusters form, and between the filaments, voids open up. Every void in the universe is bordered by walls of galaxies. Every void has filaments threading along its edges. What the tube inside the Boötes void represents is likely the remnant of one of those filaments, a sliver of the cosmic web that used to separate two or more smaller voids. When those smaller voids merged into the single enormous structure we call the Boötes void today, most of the material between them drained away. But a thread survived, a line of galaxies caught between the merging voids, preserved in the center like a fossil. This tells scientists something crucial about how the void formed. The Boötes void probably did not start as one massive hole. It likely started as several smaller voids, each maybe 50 to 100 million light-years across. Over billions of years, gravity pulled matter away from each of those regions into the surrounding filaments and superclusters. The voids grew. Their edges met. They merged. Think of soap bubbles. When two soap bubbles touch, the wall between them vanishes and they become one larger bubble. The merger is almost instantaneous for bubbles. For cosmic voids, it takes hundreds of millions of years. But the geometry is similar. The Boötes void is what happens when cosmic soap bubbles merge at a scale that borders on incomprehensible. And the tube of 60 galaxies is the leftover wall from one of those mergers, a ghost of the structure that used to separate individual voids before they became one. What makes this even more fascinating is that those 60 galaxies are among the most isolated objects in the known universe. No large galaxy cluster sits within hundreds of millions of light years of them. No dense filament runs nearby to deliver fresh gas for star formation. They are stranded in the middle of the biggest near-emptiness humans have ever mapped, and that isolation changes them. Galaxies in crowded clusters interact constantly. They merge, strip gas from each other, trigger starbursts, and slow each other down gravitationally. Galaxies in the void interior have none of that. They evolve alone, following their own quiet rhythm, shaped entirely by their own internal physics. Some studies suggest void galaxies form stars at unusual rates compared to cluster galaxies. Some appear to have different shapes. The loneliness of the void is not just a visual fact. It is a force that reshapes the galaxies living inside it. And what shaped the void itself goes back even further than gravity. It goes back to the very first instant the universe existed. Picture the universe as a sponge. The solid parts of the sponge are where matter lives: galaxies, stars, gas clouds, dark matter halos, all of it compressed into sheets and strings. The holes in the sponge are the voids, empty, vast, and everywhere. This structure has a name. Scientists call it the cosmic web, and it is the largest known structure in the universe, a single interconnected network of filaments and sheets spanning the entire observable cosmos. The filaments are the threads, long strings of galaxies and gas connecting massive clusters at their intersections. Some filaments stretch hundreds of millions of light years from one cluster to another. They are the highways of the cosmic web, carrying matter toward the densest regions. The sheets are the walls, flat, roughly two-dimensional surfaces of galaxies forming the edges of voids. When you look at a three-dimensional galaxy map, you see these walls curving around the voids, like the surfaces of bubbles pressed together. And then there are the voids, the holes in the sponge, regions where matter thinned out over billions of years as gravity pulled it toward the filaments and walls. Most voids are between 30 and 300 million light-years across. Most are threaded with a few faint filaments and scattered galaxies. The Boötes void is an extreme outlier even among voids, a region so empty and so large that it stands apart from everything else scientists have mapped. The cosmic web did not appear fully formed. It grew. It is still growing. And the engine behind its growth is gravity, acting on something almost impossibly ancient. When the universe was less than a second old, it was nearly perfectly smooth. Hot plasma filled all of space, almost uniformly. But almost is the key word. There were tiny fluctuations, microscopic ripples in the density of that plasma, left over from the quantum foam of the first moments. One region might have been 100,000th denser than its neighbor. That seems like nothing. Over hundreds of millions of years, it became everything. Gravity amplified those tiny differences. Slightly denser regions pulled in more matter from their surroundings. As they grew denser, they pulled harder. Matter flowed toward them, draining from the regions between them. Those in-between regions became the seeds of voids. The dense regions became the seeds of filaments and clusters. The cosmic web is the grown-up version of those infant ripples. Every filament, every supercluster, every wall of galaxies traces back to a fluctuation smaller than an atom that existed in the first fraction of a second after the Big Bang. And every void, including the Boötes void, traces back to a region where those fluctuations were slightly weaker, a patch of early universe that was just a hair less dense than its neighbors. That tiny deficit, amplified over 13 billion years of gravity and cosmic expansion, produced a hole 330 million light-years wide. The Boötes void is a monument to a ripple so small it is almost nothing, and that ripple, magnified by time, became the largest near-empty region humanity has ever found. But gravity alone cannot explain the full picture, because something else is at work in the universe, something that pushes instead of pulls, and its fingerprints are all over the voids. Go back 13.8 billion years. The universe is less than 1 second old. There are no stars, there are no galaxies. There is no empty space in any useful sense, because the entire volume of what will become the observable universe is packed into a region unimaginably smaller than it is today. Everything is plasma. Incredibly hot, almost perfectly smooth, almost perfectly uniform plasma. Almost. Inside that plasma, quantum mechanics was doing something that would shape every structure in the cosmos. At the quantum level, the fabric of space is never perfectly still. Tiny fluctuations pop in and out of existence constantly, energy borrowing from the vacuum and paying it back almost instantly. In the first sliver of a second after the Big Bang, those quantum ripples were frozen into the fabric of space itself as the universe expanded rapidly. They became permanent variations in density, one region with slightly more matter than average, one region with slightly less. The differences were tiny, We are talking about 1 part in 100,000. If you flatten the plasma of the early universe into a map, the peaks and valleys of density would look completely smooth to any instrument less precise than the best satellite telescopes ever built. Yet those microscopic peaks and valleys became everything. A slightly denser patch pulled in neighboring matter through gravity. As it grew denser, it pulled harder. Over millions of years, it became a filament. Over hundreds of millions of years, it became a galaxy cluster. Over billions of years, it became a supercluster. The slightly underdense patches lost matter to their neighbors and kept losing it. They expanded. They cooled. They became voids. This process has a name. Scientists call it gravitational instability. It is the mechanism by which a nearly featureless baby universe grew into the ornate cosmic web we see today. Every galaxy you have ever seen in a photo traces its origin to one of those ancient quantum ripples. Every void, including the Boötes void, traces to a region where the ripples were slightly weaker than average. The Boötes void is a quantum fluctuation that grew for 13 billion years. Satellites, like the Wilkinson Microwave Anisotropy Probe and the Planck Space Telescope, mapped those original ripples directly. They pointed at the oldest light in the universe, a faint glow left over from 380,000 years after the Big Bang, and measured its temperature variations across the sky. The map they produced shows the blueprint of the cosmic web. Every hot spot in that map corresponds to a region that became a cluster or filament. Every cold spot corresponds to a region that became a void. The pattern of the Boötes void is written into that ancient light. Its origin is encoded in the temperature map of the universe's infancy. But just knowing the origin does not explain the size. Quantum fluctuations produced voids at every scale. Smaller voids are everywhere. So why is Boötes so enormous? Why did one region end up so much emptier than its neighbors? The answer involves a process scientists are still studying, and it begins with gravity doing something that seems contradictory, pulling matter out of some regions so completely that the remaining space does something unexpected. It merges. Gravity pulls things together. Everyone knows that. But gravity also empties things out. That part is less obvious, and it is the process that carved the Boötes void into the shape it has today. Here is how it works. In the early universe, matter was spread almost evenly across all of space. Then the quantum fluctuations from the first moments gave some regions a slight head start. Those regions pulled in nearby matter. As they grew, they pulled harder, and the regions they pulled matter from grew emptier. Think of a bathtub draining. The water does not disappear. It moves. It flows toward the drain, pulled by gravity. The regions near the drain get fuller. The regions far from the drain get emptier. The bathtub, which started with water distributed across its floor, ends up with all the water concentrated around and in the drain. The cosmic web works the same way, but in 3 dimensions and at scales millions of times larger than any bathtub. The filaments and clusters of the cosmic web are the drains. Matter flowed toward them from the surrounding regions over billions of years. The voids are the places that got drained. They started slightly underdense and grew more underdense as their matter bled away into the surrounding filaments. For the Boötes void, this draining process ran for billions of years against a backdrop of several surrounding superclusters. The Shapley supercluster, the Hercules supercluster, the Corona Borealis supercluster. These are among the most massive concentrations of galaxies known. They sit around the Boötes void, like walls around a courtyard, and for billions of years, they have been pulling matter toward themselves, draining the void deeper and deeper. The void did not form because something erased the galaxies. No catastrophe struck. No force wiped the region clean. The galaxies that would have formed there never got the chance, because the matter they would have formed from drained away into the filaments and superclusters surrounding the void before it could cluster into galaxies. This is a subtle but important distinction. The Boötes void is empty because gravity moved matter away from it. Every galaxy in every supercluster surrounding the void is built partly from matter that used to sit in that empty region. The void and the walls around it are two sides of the same process. Now here is the part that gets strange. As voids drain and grow emptier, something else starts to dominate inside them. With less matter present to slow it down, a different force takes over. A force that pushes instead of pulls. A force that makes the void expand even faster than the surrounding universe. Scientists did not know this force existed until 1998. When they discovered it, they called it dark energy. And its relationship with cosmic voids is one of the most important and least understood problems in modern physics. The void is not just an empty space, it is a laboratory. And what is happening inside it right now is pushing the boundaries of what science can explain. The Boötes void probably did not begin as one hole. That is the leading explanation among cosmologists today, and it changes how you picture the void's history. Instead of a single enormous empty region that formed all at once, the Boötes void is almost certainly the product of a slow collision, a merger of smaller voids that grew together over billions of years until their borders touched and they became one. This idea comes directly from looking at the 60 galaxies inside the void and the tube shape they trace through its center. That tube is not random. It is the signature of a boundary that used to exist. A wall of galaxies that once separated two or more smaller voids before those voids expanded enough to swallow the wall between them. Picture two growing bubbles side by side. Each one expands as matter drains from its interior into the surrounding cosmic web. Eventually, the bubbles grow large enough that their edges meet. The thin wall between them, a sheet of galaxies that had been sitting at the boundary, gets absorbed into the interior of the merged bubble. Some of those galaxies survive the merger. They end up stranded in the middle of the new, larger void, tracing the path of the old boundary. That is likely what the tube of 60 galaxies inside the Boötes void represents. A fossilized wall, a remnant of a boundary that vanished when the voids on either side grew large enough to merge. Computer simulations support this picture. When scientists run models of cosmic structure formation, the largest voids in the simulations almost always form through exactly this process. Smaller voids expand, touch, and merge repeatedly, building up supervoids step by step, the way rivers build deltas. The simulated supervoids that result look strikingly similar in shape and galaxy content to the Boötes void. The number of smaller voids that contributed to the Boötes void is still uncertain. Some estimates suggest it formed from the merger of roughly 3 to 5 individual voids, each comparable in size to the largest typical voids found elsewhere in the universe. Others suggest more. The details are hard to pin down because the merger happened billions of years ago, and the evidence inside the void is limited to those 60 lonely galaxies. But the general picture is solid. The Boötes void is the cosmic equivalent of many smaller empty regions combining into one enormous empty region over billions of years. And that process is still happening. The void is still growing. Matter is still draining from its interior. Its borders are still pressing outward, slowly, into the surrounding cosmic web. The 60 galaxies inside it are still being pushed apart from one another as the void expands. In a billion years, the interior of the Boötes void will be even emptier than it is today. The tube of surviving galaxies will be more stretched, more isolated, each galaxy farther from its neighbors. And if you could watch the surrounding superclusters over the same timescale, you would see them growing denser and more massive as the matter from the void continues to flow into them. The void and the walls around it are still in conversation. Matter is still moving. The process that created the Boötes void is ongoing. What stopped some astronomers from accepting this clean picture for years was not the physics, it was the size. Even with mergers accounted for, a void 330 million light-years across seemed like too much. And when scientists finally figured out why the merger process could produce something that large, the answer brought a new mystery with it. When Kirshner's team first identified the Boötes void in 1981, they were working with a relatively small dataset. The technology of the time limited how many galaxies they could survey and how faint those galaxies could be. Their estimate of the void's galaxy population was rough. Over the following decades, that changed. Better telescopes, larger surveys, more sensitive instruments. Each new generation of equipment let astronomers peer deeper into the void and count more carefully. By the early 2000s, the census of galaxies inside the Boötes void was far more refined than anything Kirshner's team could have produced. The result was not reassuring. The updated count confirmed roughly 60 galaxies with well-established positions inside the void. Some surveys hinted at a few more faint candidates at the edges of detection, but the core number, the confirmed, well-mapped galaxy count inside the void's volume, stayed brutally low. To understand how shocking that number is, consider what the average cosmic density would predict. Take a sphere 330 million light-years across and place it at random anywhere in the observable universe. On average, that sphere should contain roughly 2,000 galaxies of the brightness level astronomers can detect. Some regions of space are denser and would show more. Some are less dense and would show fewer. But a random sphere of that size, placed in a typical patch of the cosmos, should hold around 2,000 galaxies. The Boötes void holds 60, confirmed. That is about 3% of the expected number. The void is not slightly underdense. It is not half empty or a quarter full. It is more than 95% below the average. For context, if a city with a normal population of 200,000 people were hit by whatever process created the Boötes void, the surviving population would be around 6,000 people scattered across the entire city, and those 6,000 would be grouped in one corridor, not spread across the city, clustered along a single street. That is what the tube of 60 galaxies represents. Almost all the surviving matter inside the void is concentrated along one line, one fossilized filament. The rest of the volume holds virtually nothing detectable. Astronomers have not stopped searching. The question of whether very faint, small galaxies might be hiding inside the void is still open. Some researchers believe the count of 60 undercounts the true total because the smallest galaxies are too dim to show up in existing surveys. Deep imaging programs have targeted parts of the void looking for faint dwarf galaxies or diffuse gas clouds. So far, the searches have added very little to the official count. The void appears genuinely and stubbornly empty. That emptiness matters beyond the simple shock of the numbers. The galaxy deficit inside the Boötes void is the clearest visual confirmation that cosmic voids are real structures with real physical consequences. The universe is measurably, dramatically uneven on the largest scales. And that unevenness is not a bug, it is a feature. It is the direct result of the same physics that built galaxies, stars, and planets. But what happens to the galaxies that do survive inside the void? How does living in almost total isolation for billions of years change a galaxy? The answer turns out to be more interesting than anyone expected. A galaxy that forms in a dense cluster lives a violent life. It gets pulled toward neighbors. It merges with smaller galaxies that fall into it. Streams of gas pour in from the surrounding cosmic web, feeding star formation in bursts. Other galaxies strip material from it as they pass close. The environment is constant chaos, and that chaos shapes the galaxy deeply. Many cluster galaxies are giant, elliptical, and old. They burned through their gas early in intense star-forming episodes, and now drift as enormous collections of ancient stars, no longer making new ones. The 60 galaxies inside the Boötes void live a completely different kind of life. With no massive neighbors nearby, they do not merge. No galaxy is close enough to interact with meaningfully. No dense filament feeds them a steady stream of fresh gas. The intergalactic medium inside the void is thinner and cooler than in the surrounding cosmic web. These galaxies are on their own, evolving according to their own internal physics, uninterrupted by outside forces for billions of years. Studies of void galaxies from other, better-studied voids give scientists their best current picture of what isolation does. and the results are surprising. Void galaxies tend to be smaller than average. They tend to have more spiral structure than elliptical structure, because without mergers, they never get scrambled into featureless blobs. They tend to have more ongoing star formation relative to their mass. Stars are still forming inside them at rates that would seem unusual for galaxies of their size in denser environments. The reason likely comes down to gas. Cluster galaxies lose their gas through interactions, tidal stripping, and the hot medium of the cluster environment. Void galaxies hold onto their gas. With no neighbors stealing it and no violent encounters heating it and blowing it away, the gas stays inside the galaxy and keeps forming stars at a slow, steady pace. In dense environments, galaxy evolution runs fast and burns out. In the void, it runs quietly and lasts longer. The galaxies inside the Boötes void are probably among the most isolated star-forming systems in the observable universe. Each one has been forming stars at its own unhurried pace, surrounded by darkness, without a neighbor close enough to interact with on any meaningful timescale. For a civilization living in one of those galaxies, the universe would look remarkably empty. The nearest large galaxy might be hundreds of millions of light years away. The night sky, even with the most powerful telescopes imaginable, would show far fewer external galaxies than our own sky does. The cosmic web would be visible in principle, but its nearest elements would be impossibly remote. That isolation might seem limiting, but it also means no collisions, no tidal disruptions, no galaxy mergers disturbing civilization for billions of years. A quiet neighborhood, the most extreme quiet neighborhood in the known universe. And the most extreme version of that isolation raises a question that scientists have actually explored with real calculations. What if our Milky Way had formed inside the Boötes void instead of where it actually did? The answer is one of the most thought-provoking ideas in modern astronomy. Imagine the Milky Way sitting at the center of the Boötes void. Everything about our galaxy would be the same. The same 400 billion stars, the same spiral arms, the same black hole at the center, the same Earth, in the same orbit around the same Sunday. But the view from Earth would be fundamentally different, and that difference would have changed the entire history of human science. On a clear night from Earth, our sky is full of distant galaxies. The Andromeda galaxy is visible to the naked eye as a faint smudge 2.5 million light-years away. With a telescope, thousands of galaxies come into view. With the best telescopes humanity has built, hundreds of billions of galaxies populate the observable universe. From inside the Boötes void, the nearest galaxy to our hypothetical Milky Way might be tens or hundreds of millions of light-years away. The faint smudge of Andromeda would not exist on our sky. The local group of galaxies, the cluster our Milky Way actually belongs to, would be absent. The nearest concentration of galaxies would be the superclusters at the void's edge, hundreds of millions of light-years away, visible only as the faintest possible specks, even through the most powerful imaginable telescope. Scientists who have worked through this scenario reach a striking conclusion. If the Milky Way had formed inside the Boötes void, humanity might not have discovered that other galaxies exist until the mid-20th century at the earliest. And even then, the evidence would have been far harder to gather. The discovery that the universe extends far beyond our own galaxy, made by Edwin Hubble in the 1920s using relatively modest equipment, depended on having nearby galaxies close enough to resolve individual stars inside them. From inside the void, those galaxies would be too far away for that technique to work with anything short of technology far beyond what existed in the 1920s. The realization that the universe is expanding might have come far later too. Hubble measured the recession of nearby galaxies to establish the expansion rate. From inside the void, the nearest galaxies would be receding so fast, so far away, that early measurements would have been far harder to interpret. Cosmology as a science might have been delayed by decades or a century. This thought experiment highlights something profound. Our scientific knowledge of the universe depends partly on where we happen to be inside it. We were born in a relatively busy neighborhood with enough nearby galaxies to give early astronomers the raw material for discovery. Scientists inside the Boötes void would have started with almost none of that, and there is a real version of this scenario playing out right now. Our Milky Way does not actually sit in a typical patch of the cosmic web. We live on the edge of our own, smaller void, and that fact is quietly causing one of the biggest problems in modern physics. The Milky Way is not in a dense cluster. Look at a large-scale map of the local universe, the region within a few billion light-years of Earth, and a pattern emerges. Our galaxy sits near the edge of a relatively underdense region. Scientists call it the KBC void, named for the researchers who mapped it most carefully. Others call it the local hole. It is not anywhere near the scale of the Boötes void. The local hole spans roughly 1 billion light-years across, and the density inside it is only somewhat below the cosmic average. It is a mild underdensity, not an extreme supervoid, but it is real, and its reality matters. For a long time, cosmologists assumed the Milky Way sat in a typical patch of the cosmic web. Standard calculations of how the universe behaves were built on that assumption. Distances, expansion rates, and galaxy counts were all interpreted assuming our local environment was average. The local hole calls that assumption into question. Here is why it matters. Inside a void, galaxies experience a slightly different gravitational environment than galaxies in a dense filament or cluster. The lack of surrounding mass means the gravitational pull from the void's walls dominates. This causes galaxies inside the void to drift outward toward the walls, slightly faster than galaxies in a typical region would move. From inside the void, that extra outward motion looks like an elevated expansion rate. Measure the recession speed of galaxies around you and convert it into an expansion rate for the universe, and you get a number slightly higher than you would get if you made the same measurement from a typical patch of the cosmic web. This is not a small problem. One of the most intense debates in modern cosmology involves exactly this number, the Hubble constant, which describes how fast the universe expands. Two methods of measuring it give two different answers. The disagreement is called the Hubble tension, and it has troubled physicists for years. Some researchers have proposed that living inside the local hole partially explains the discrepancy. Our position inside an underdense region might make the local expansion rate appear slightly inflated compared to what you would measure from a random position in the cosmos. The debate is ongoing. Most cosmologists think the local hole alone cannot fully explain the tension, but the fact that our location in an underdense region measurably affects our measurements of the universe is a sobering reminder. Where you stand in the cosmic web shapes what you see. The Boötes void, as an extreme version of what we already live near, amplifies every one of these effects. The galaxies inside the Boötes void experience an even more extreme version of this drift. The expansion inside the void runs faster than the cosmic average. The gravitational environment is dominated almost entirely by the distant surrounding superclusters. And that gravitational environment, that unusual expansion behavior inside the void, is precisely why the Boötes void has become one of the most valuable laboratories in all of cosmology. The void is not just an empty region, it is a window into physics that dense environments hide, and one of the strangest things hiding in that window involves a force that should not be there. The universe has a speed limit, sort of. Everything in the universe is moving away from everything else because space itself is expanding. The rate of that expansion, the Hubble constant, is one of the most important numbers in all of physics. It tells us the age of the universe, its ultimate fate, and the scale of everything inside it. Measuring it should be straightforward. You measure the recession speed of distant galaxies, compare it to their distance, and get the rate. Physicists have two independent ways to do this. One looks at the early universe, using the ancient light of the cosmic microwave background to calculate what the expansion rate should be today. The other looks at the nearby universe, measuring actual galaxies and using them as rulers. The problem is that the two methods disagree. By a lot, the nearby measurement gives a higher expansion rate than the early universe measurement. The gap between the two results is too large to blame on measurement error. Physicists have checked the numbers repeatedly for more than a decade. The disagreement holds. This is the Hubble tension, and it is one of the most embarrassing unsolved problems in modern physics. The embarrassing part is not just that the numbers disagree, it is that the standard model of cosmology, which has successfully explained almost everything else scientists have thrown at it, cannot account for the gap. If the standard model is correct, both measurements should give the same answer. They do not. Several possible explanations are in play. Some researchers think the early universe contained exotic particles or energy forms not currently in the models. Others think the nature of dark energy may be more complicated than the simple constant it is usually assumed to be. Others point to the local hole, the underdense region our Milky Way sits near, as a partial contributor. The Boötes void connects to this debate directly. Inside supervoids, the expansion of space runs faster than average because there is less matter to slow it down. Galaxies inside the void drift outward toward the dense walls surrounding it, adding an extra component to their recession speed. If early measurements of the universe's expansion rate were made from inside or near a large void, the results would appear inflated compared to the true cosmic average. Researchers have studied whether the scale of the local hole and the Boötes void type of environments could, taken together, explain the Hubble tension. The current consensus is that the local hole contributes something to the discrepancy, but probably cannot account for the full gap on its own. The Hubble tension likely points to something deeper, new physics, possibly, a gap in the standard model that the numbers are forcing into view, and supervoids like the Boötes void are part of the toolkit scientists are using to probe that gap. Because the void's unusual expansion behavior is a measurable, testable phenomenon. How fast the void grows, how galaxies on its rim behave, how light passing through the void changes. All of those are sensitive probes of dark energy and the expansion rate. The more precisely scientists measure the Boötes void, the more precisely they can test the models that the Hubble tension is threatening to break. And the telescope mission being used to make those measurements is the most ambitious mapping project in the history of astronomy. Here is a number that reframes everything. Cosmic voids occupy roughly 80% of the volume of the observable universe. Read that again. 80%. The galaxies, the clusters, the filaments, the superclusters. All the matter in the cosmic web packed together takes up only about 20% of the universe's total volume. The remaining 80% is void, empty space, near nothingness, on a scale that makes every galaxy, every star, every planet, every atom of matter in existence, a thin skin stretched across the surface of an ocean of emptiness. This is not an approximation. This is what galaxy surveys show directly. When astronomers map the three-dimensional distribution of galaxies and calculate what fraction of the universe's volume falls inside voids versus inside filaments and clusters, the result is consistently around 80% void. The universe, seen at its largest scales, is almost entirely empty. This flips the intuition most people bring to astronomy. When you look at a photo of a galaxy cluster, the image is dense with glowing objects. Stars, nebulae, galaxies, stacked on top of galaxies. It looks full, crowded. The universe seems like a busy place. But those photos are pointing at the 20%, the regions where matter concentrated. The cameras are aimed at the rare, dense patches. The 80% of empty space between those patches looks like nothing because it is, by definition, almost nothing. There is very little to photograph. If you could somehow take a photograph of the universe from outside, pointed at a random direction, your image would show void, probably nothing recognizable. The chance of your random pointing landing on a galaxy or filament is only about 1 in 5. The Boötes void is an extreme example of the dominant feature of the universe, and this creates a philosophical puzzle that cosmologists sit with. The 80% is not dead space, it is active space. Dark energy is filling it, pushing it outward, making voids grow larger over time. Faint radiation passes through it constantly. The laws of physics operate inside it exactly as they do inside the densest galaxy clusters. Voids are not the absence of the universe. They are the universe's most common state. The matter we are made of, the planets, stars, galaxies, the entire cosmic web, is the unusual part. We are the rare exception inside a cosmos that is overwhelmingly, structurally, fundamentally empty. That emptiness is not random. It grew from the same quantum ripples that built every galaxy. The void and the filament are siblings, produced by the same process, one getting denser and the other getting emptier as the same gravitational machinery ran for billions of years. Understanding voids means understanding the dominant volume of the cosmos, and there is a measurement technique that turns the void's emptiness into a precision scientific tool, a way of reading the universe's deepest secrets from the absence of galaxies rather than their presence. The tool involves light, the oldest light in the universe. And what happens to that light as it crosses a void reveals something that should not be possible to measure but is. The Boötes void does not look like anything on a regular photograph. Point a telescope at the region of sky where it sits, and you will see a normal field of stars. Most of those stars are inside our own Milky Way galaxy, just a few thousand light-years away. Background galaxies dot the image too, glowing faintly at enormous distances. The view is unremarkable. This confuses people. The Boötes void is one of the largest structures ever identified in the universe, yet there is no iconic image of it. No dramatic black circle on the sky. No visible absence to stare at. The reason is that the void exists in 3 dimensions, and our telescopes only directly capture 2. When you look at a patch of sky, you see everything along your line of sight stacked together. A galaxy 2,000 light-years away, a galaxy 2 million light-years away, and a galaxy 2 billion light-years away all appear in the same direction. They layer on top of each other from our perspective. A void at 700 million light-years does not remove the stars in front of it or behind it. It only removes galaxies at a specific distance, between about 500 and 850 million light-years away in that direction. From a 2-dimensional photo, you cannot tell the difference between no galaxies at this distance along this direction and galaxies everywhere at all distances. To see the Boötes void, you need the 3rd dimension, and the only way to get that 3rd dimension is redshift. Redshift reveals the distance. Once you have the distance, you can plot each galaxy in 3-dimensional space. Then the void jumps out immediately. A sphere-shaped region, hundreds of millions of light-years across, almost devoid of galaxies at the right distances, surrounded by denser regions on all sides. There is also a common confusion between the Boötes void and a very different object called Barnard 68. Barnard 68 is a dark molecular cloud, about 400 light-years from Earth, inside our own galaxy. It is a dense knot of cold gas and dust that absorbs the light from background stars completely, producing a dark circle on the sky with no stars visible inside it. Photos of Barnard 68 circulate widely on the internet, mislabeled as images of the Boötes void. The confusion is understandable. Barnard 68 looks like a hole in space, but it is a physical object, not an absence. It blocks light from behind it rather than being a region of genuinely reduced matter. The Boötes void, by contrast, lets light from background galaxies pass through it freely. Photons cross it without obstruction. The void is transparent. The only photographic signature of the Boötes void is statistical. Look at thousands of galaxy positions in that region. Compare them to what you find in similar regions elsewhere in the sky, and the deficit becomes undeniable. The void is visible in the data, in the pattern of absences across a huge 3-dimensional volume. Absence is actually a powerful scientific tool. In this case, it has revealed something about the universe that a full sky of galaxies could never have shown. And a satellite launched specifically to exploit that absence is now measuring the void with a precision Kirshner's team could not have imagined in 1981. But before that, there was a moment in the 1990s when the Boötes void nearly broke the models of the universe entirely, and the fight over whether it could exist at all became one of the most contentious debates in the history of cosmology. For most of the 1980s, the Boötes void was a problem without a solution. It was confirmed, it was real, and it was too big. The models of structure formation available at the time predicted voids, but small ones. Gravity, acting on cold dark matter, could build filaments and clusters over billions of years. It could hollow out modest empty regions as matter drained toward the growing structures. But running the simulations with the parameters scientists trusted, no void came out anywhere near the size of the Boötes void. The numbers were unambiguous. A void 330 million light-years wide required more time to form under the standard gravitational mechanisms than the universe had existed. If the models were right, the Boötes void should not be there. And yet there it was. The debate that followed was sharp. One camp argued that the surveys must be flawed. The redshift technique had known limitations. Maybe the apparent void was a statistical artifact of the survey geometry. Maybe the team had happened to scan a region underrepresented by the particular angles they chose. Reanalyzing the survey data, this camp argued, might make the void shrink to a more acceptable size. A second camp argued that the models needed revision. Perhaps dark matter behaved differently at large scales than simulations assumed. Perhaps the initial fluctuations in the early universe had more power at certain scales than the standard picture predicted. Perhaps an unknown ingredient was missing from the equations. A third, quieter group raised a more radical possibility. Maybe the universe was simply older than current estimates, which would give gravity more time to carve out a structure that size. This idea bumped into other well-established constraints, but it was taken seriously enough to be published and debated. Every proposed resolution ran into obstacles. Follow-up surveys kept confirming the void. Revised models incorporating known uncertainties could not comfortably produce a structure that large. The quiet alarm from 1981 became an ongoing tension in the literature. Then, in the 1990s, two things happened almost simultaneously. Computers became powerful enough to simulate the formation of large-scale structure in much greater detail. Researchers could now run simulations that tracked hundreds of millions of particles of dark matter through billions of years of gravitational evolution, producing three-dimensional maps of simulated universes that could be compared directly to observations. Those simulations, run under the standard cold dark matter model, produced large voids. Not every run produced something as extreme as the Boötes void, but extreme cases appeared. Occasionally, the simulated universe grew a supervoid of comparable size. And then, in 1998, a separate discovery changed everything. Astronomers studying distant supernovae found evidence that the expansion of the universe was accelerating. Something was pushing space apart faster and faster over time. That something was dark energy, and its inclusion in the cosmological model dramatically changed what simulations could produce. With dark energy added, voids grew faster. The accelerating expansion of space pushed void regions apart more aggressively than gravity alone could account for. Simulations with dark energy produced supervoids more readily, and the Boötes void moved from impossible anomaly to dramatic but explainable outlier. The crisis quietly resolved. The Boötes void stayed where it was, unchanged. The models came to it, and dark energy, the force that saved the explanation, turned out to be most visible precisely inside voids, like the one that forced scientists to find it. In the early 1990s, a group of physicists sat down with some of the most powerful computers available and tried to grow a universe from scratch. They started with a nearly smooth box of dark matter particles. They gave each particle a tiny random nudge, mimicking the quantum fluctuations from the first moments after the Big Bang. Then they let gravity run. For simulated billions of years, they watched the particles move, cluster, and organize. What emerged was not a smooth, uniform distribution. The particles formed webs, threads of high-density material stretched across the simulation box. Dense nodes appeared where threads crossed, and between the threads, clearing as matter drained away, large, empty regions opened up. The simulations were growing a cosmic web. This was a turning point. For the first time, scientists could directly compare what their models predicted the large-scale structure of the universe should look like against what telescopes actually observed. And the match, while imperfect, was striking. Filaments appeared in roughly the right places. Clusters formed at roughly the right scales. Voids opened up in the simulated universe with roughly the right frequency and size range. Roughly. The Boötes void was still a problem. Early simulations under the cold dark matter model produced voids, but rarely produced anything as extreme as 330 million light-years across. The simulated universes had large voids, but the largest were usually smaller than the Boötes void. The simulations were good, but they seemed to be missing something. Then dark energy entered the picture. When the 1,998 supernova discoveries revealed that the expansion of the universe was accelerating, theorists immediately updated their simulations to include a dark energy term. The effect on void formation was dramatic. Dark energy does not act equally everywhere. In dense regions, where matter is packed tightly and gravity is strong, dark energy's push is overwhelmed by gravity's pull. Clusters and filaments keep forming despite dark energy. But in underdense regions, where gravity is weak and matter is thin, dark energy's push dominates. It accelerates the local expansion of space. It drives matter away from the void's interior more aggressively. Voids grow faster and larger than they would under gravity alone. When scientists added dark energy to their simulations, the maximum size of voids in the simulated universe jumped. Supervoids comparable to the Boötes void began appearing in the simulations with a frequency consistent with having one or two such structures in the observable universe. The Boötes void stopped being an impossible outlier and became a rare but expected feature of a universe containing dark energy. The simulation had saved the standard model. Or rather, dark energy had saved it, and the simulation made that clear. This was a quiet but profound moment in cosmology. A structure that seemed to break the laws of physics in 1981 turned out to be one of the clearest early confirmations that a completely unknown force, dark energy, was reshaping the cosmos on its largest scales. The Boötes void pointed toward dark energy, before dark energy had a name, and the connection between voids and dark energy runs deeper than just the formation of supervoids. It runs into one of the most precise and subtle measurements in all of physics. A measurement made using light so old it predates every galaxy in the universe. Dark energy is invisible. It produces no light. It interacts with nothing in any way scientists can directly detect. Its existence was inferred from the motion of distant supernovae, not from any instrument that touched it or any photograph that captured it. For a force that makes up roughly 68% of the total energy content of the universe, dark energy is extraordinarily elusive, but it leaves fingerprints, and one of the clearest fingerprints dark energy leaves is imprinted on light that passes through cosmic voids. Here is the mechanism. The oldest light in the universe is the cosmic microwave background, the faint glow of radiation left over from about 380,000 years after the Big Bang. This light has been traveling through space for nearly 13 billion years. It fills the sky uniformly from every direction, a fossil of the early universe, still faintly detectable with sensitive microwave telescopes. As this ancient light travels, it passes through the large-scale structure of the universe. It crosses filaments and superclusters. It crosses voids. And crossing a void does something subtle to it. When a photon, a particle of light, enters a void, it falls into a gravitational well. The void's walls, The surrounding superclusters create a region of slightly lower gravitational potential at the void's center. Falling into that well gives the photon a tiny energy boost, the same way a ball rolling into a dip gains speed. Crossing the void and climbing back out of the well on the other side should cost the photon exactly that same energy, leaving the photon unchanged. But in a universe with dark energy, the void does something unexpected while the photon crosses it. Dark energy makes the void expand. The gravitational well gets shallower while the photon is inside it. The photon fell into a deeper well than the one it climbs out of. It gains more energy entering than it loses exiting. The photon comes out of the void with a tiny energy surplus. From our perspective, that surplus appears as a slight warming of the cosmic microwave background in the direction of the void. This effect is called the integrated Sachs-Wolf effect. It is one of the most direct observational signatures of dark energy in the universe, and supervoids like the Boötes void produce measurable versions of it. Scientists have searched for this signal in the direction of the Boötes void and other large voids. The measurements are difficult because the effect is tiny, a temperature shift of a few millionths of a degree against a background that is already only 2.7 degrees above absolute zero. But the signal is detectable, and it matches what dark energy models predict. Every time a photon crosses the Boötes void, dark energy writes a small message onto it. Astronomers read those messages with microwave telescopes. The messages confirm that dark energy is real, is present, and is actively reshaping the void right now. What dark energy will do to the void over the next tens of billions of years is even more striking. And the picture of where the universe is heading, driven by what the Boötes void is already showing us, is one of the most unsettling forecasts in the history of science. The neutrino weighs almost nothing. It is one of the most abundant particles in the universe. Every second, roughly 100 trillion neutrinos pass through your body without interacting with a single atom. They travel at nearly the speed of light. They pass through the entire Earth as if it were not there. They are produced by the sun, by nuclear reactors, by supernovae, by the Big Bang itself. And they weigh almost nothing. Scientists know this. What they do not know is exactly how much almost nothing weighs. Measuring the mass of a neutrino is one of the most difficult problems in experimental physics. Laboratory experiments have established upper limits. The neutrino mass is less than a tiny fraction of the mass of an electron, itself already a very light particle. But pinning down the exact mass has resisted every direct measurement attempt so far. Cosmic voids have entered this problem in an unexpected way. Neutrinos, despite their tiny mass, exist in enormous numbers. The total mass of all the neutrinos in the universe, added together, is a meaningful fraction of the total matter budget of the cosmos. And because neutrinos have mass, they respond to gravity. They flow toward dense regions and away from voids, just like other matter, though far more weakly because their mass is so small. The mass of the neutrino affects how voids grow. Heavier neutrinos damp out small-scale structure more efficiently. They smooth out density fluctuations on scales where they're free-streaming. Their tendency to travel long distances without interacting washes out small clumps of matter. This affects the shapes and sizes of voids in a subtle but measurable way. More massive neutrinos produce voids with slightly different statistical properties than less massive neutrinos. By measuring the size distribution of voids across the sky and comparing those measurements to simulations run with different assumed neutrino masses, scientists can constrain what the neutrino mass must be. The Boötes void alone is too singular to give a precise neutrino mass measurement, but catalogues of thousands of voids, including supervoids in the same class as Boötes, carry enough statistical signal to put meaningful limits on neutrino mass from cosmic structure alone. This is a remarkable idea. The largest near-empty structures in the universe are sensitive to the mass of the smallest known massive particles. The cosmic and the subatomic are connected through the physics of void formation. Building a catalogue of voids large enough to make precise neutrino mass measurements requires mapping enormous volumes of the universe. redshift surveys of tens or hundreds of millions of galaxies, three-dimensional maps spanning billions of light-years. That level of mapping was out of reach for most of astronomy's history. It is now underway. A space telescope launched in 2023 has begun building exactly that catalogue, and when it finishes, what it reveals about dark energy, neutrino mass, and the nature of the largest structures in the universe will either confirm our models or force a crisis bigger than anything the Boötes void created in 1981. In July 2023, a spacecraft lifted off from Cape Canaveral carrying instruments designed to solve some of the deepest mysteries in cosmology. The Euclid Space Telescope, built by the European Space Agency with contributions from scientists across the world, has one central mission: map the three-dimensional positions of billions of galaxies across more than a third of the entire sky. Build the largest and most detailed atlas of the cosmic web ever assembled, and use that atlas to understand what dark energy is, how it behaves over time, and what it is doing to the future of the universe. Voids are central to that mission. A cosmic void is not just an empty space. It is a precision instrument. The size, shape, and growth rate of voids encode information about dark energy, dark matter, neutrino mass, and the overall geometry of the universe. Measure voids precisely enough, and they tell you the values of the most fundamental quantities in physics. Euclid will find and characterize hundreds of thousands of voids across the observable universe. Some will be small, typical voids tens of millions of light-years across. Some will be supervoids in the class of the Boötes void. Each one contributes a data point. Stacked together, those data points become a precision measurement of how void properties change across cosmic time. Dark energy's behavior over time is the key question Euclid is designed to answer. In the simplest version of our cosmological model, dark energy is a constant. It has the same strength today as it did a billion years ago, and will have the same strength a billion years from now. It is built into the fabric of space itself, unchanging. But there are other possibilities. Dark energy could be a field that evolves. Its strength could have been different in the past and could be different again in the future. If dark energy changes over time, the growth rate of voids should reflect that change. Voids that formed when dark energy was stronger should have grown faster than voids that formed when it was weaker. By comparing void properties across different distances, and therefore different times in cosmic history, Euclid can map how dark energy has behaved across billions of years, whether it is constant or evolving, whether it matches the simplest model or requires something new. In parallel, astronomers on the ground are continuing to refine the census of the Boötes void itself. Deeper surveys push the detection limit for faint galaxies lower, searching for small dwarf galaxies or diffuse structures hiding below earlier instruments' sensitivity. Every additional galaxy found inside the void adjusts the picture of how it formed and how it compares to simulated supervoids. Euclid has already begun releasing data. Early results have confirmed that its instruments are performing at the level required for the planned precision measurements. The full survey will take years to complete, and the full analysis will take years beyond that. But the Boötes void, the structure that threw cosmology into crisis in 1981, has become one of the benchmark objects against which Euclid's results will be tested. A hole in space, found by accident, has become a cornerstone of 21st century physics. And the strangest signal from that void has nothing to do with what is missing from it. It has to do with what ancient light does when it passes through it. The Boötes void is large, but it may not be the most extreme void in the universe. In 2004, astronomers studying the cosmic microwave background noticed something unexpected. A region of sky in the direction of the constellation Eridanus showed a patch of slightly colder temperature than the surrounding microwave background. The patch covered a region of sky much larger than typical fluctuations in the ancient light. Scientists called it the cold spot. Cold spots in the cosmic microwave background are expected. The early universe was not perfectly smooth. and the fluctuations that produced the cosmic web left their imprint on the microwave background as temperature variations. Some regions appear slightly warmer, some slightly cooler. Most of these fluctuations match the predictions of the Standard Model closely. The Eridanus cold spot did not match the predictions. It was larger, colder, and more uniform than the statistical models said it should be. Researchers ran calculations to determine how likely such a feature was to appear by chance in a universe governed by standard cosmology. The answer was uncomfortably low. The cold spot looked like an outlier. Several explanations were proposed. Some researchers suggested it was a statistical fluke, an unusual but possible random fluctuation in the ancient light. Others proposed that it could be a signature of exotic physics from the very early universe, perhaps a collision between our universe and another in a multiverse scenario. But one explanation drew the most attention from cosmologists: a supervoid, larger even than the Boötes void, sitting between Earth and the cold spot region. If an enormous underdense region lay along that line of sight, the integrated Sachs-Wolf effect described in a previous chapter would imprint a cold signature on the microwave background in that direction. A supervoid large enough to explain the cold spot would need to be roughly 1,800,000,000 light-years across, considerably larger than the Boötes void. Subsequent surveys did find a large underdense region in that direction, a structure now sometimes called the Eridanus supervoid. Whether it is large enough and empty enough to fully explain the cold spot remains an active debate. If the Eridanus supervoid is real, and is the explanation for the cold spot, it would be the largest known void in the observable universe, dwarfing the Boötes void in the same way that the Boötes void dwarfs a typical void. And if supervoids that large exist, they push the statistical limits of the Standard Model harder than anything the Boötes void alone could produce. A universe governed by cold, dark matter and a constant dark energy should produce supervoids, but the probability of producing one as extreme as the Eridanus supervoid becomes uncomfortably small. The cold spot is unresolved. The debate continues. But the Boötes void opened the door to asking whether supervoids could be the explanation for anomalies in the oldest light in the universe. And the answer to that question, whatever it turns out to be, will reshape how scientists think about the universe's larger structures. The cold spot points outward to something bigger. But there is another signal hidden inside voids, a signal that travels in a completely different direction and tells a completely different story. Light does not cross a void unaffected. This seems like it should be obvious. A void is empty. Empty space should leave light alone. But empty space in a universe with dark energy is not truly inert. The void is growing, and a photon crossing a growing void carries the evidence of that growth inscribed on its energy. The integrated Sachs-Wolf effect, introduced earlier, is the mechanism, but the details of how it works reveal something profound about the relationship between light, space, and dark energy. Picture a photon entering the Boötes void from one edge. The void is enormous. The photon will spend hundreds of millions of years crossing it, traveling at the speed of light. As it enters, it encounters the gravitational influence of the void's structure. The walls of the void, the superclusters on all sides, create a gravitational landscape. The interior of the void is a region of lower gravitational potential than the surrounding walls. Falling into that region, the photon gains energy. This is a real, measurable effect. Photons gain energy falling into gravitational wells, the same way light from a laser pointer is very slightly blue shifted when it falls toward the ground. For the Boötes void, the effect is tiny but real. Now the photon crosses the void. This takes hundreds of millions of years of travel time. During that time, dark energy is actively expanding the void. The gravitational well the photon entered is not the same gravitational well it is exiting. Dark energy has made the void larger, lower density, and shallower. The well has grown weaker while the photon was inside it. When the photon climbs back out on the far side of the void, it loses less energy than it gained entering. The net result is a tiny energy surplus, The photon arrives at a distant observer fractionally more energetic than it would be if dark energy were absent. On the map of the cosmic microwave background, this appears as a fractional warming of the background temperature in the direction of the void. Measurements of many voids stacked together, because each individual signal is extremely small, have confirmed this effect. Every photon of the cosmic microwave background that has crossed the Boötes void over billions of years carries this tiny mark. It is a signature written by dark energy on the oldest light in the universe. This measurement is one of the few direct confirmations that dark energy is actively doing something to the geometry of space right now. It is not a historical effect. It is ongoing. The Boötes void is growing at this moment, and every photon crossing it is picking up that faint dark energy imprint. The precision of this measurement depends on having large, well-characterized voids. Supervoids, like the Boötes void, produce larger signals, easier to detect above the noise. This is one reason why astronomers invest significant effort in mapping and understanding the Boötes void specifically. The void that broke cosmology in 1981 has become one of its most precise instruments, and those 60 galaxies living inside the void, the ones tracing the tube through its center, have a story of their own that goes far beyond their position in space. Their evolution, running in almost total isolation for billions of years, has produced something unusual, something that no galaxy in a dense cluster ever experiences. A galaxy in the heart of a dense cluster burns bright and burns fast. Surrounding galaxies are close enough to interact gravitationally. Gas streams in from nearby filaments. Mergers happen. Starbursts, episodes of rapid star formation triggered by collisions and gravitational disturbances, light up the galaxy for tens of millions of years. The galaxy consumes its gas quickly in these intense episodes. Eventually, the gas runs out. Star formation slows and stops. The galaxy becomes a quiet collection of old, red stars, still glowing but no longer making anything new. The galaxies inside the Boötes void never go through any of this. With no neighbors close enough to interact with, and no dense filament nearby to deliver fresh gas, these isolated galaxies sit in a state of prolonged, quiet activity. They form stars steadily, slowly, at a pace dictated entirely by their own internal gas supply. No starburst ever ignites. No merger ever scrambles their structure. No ram pressure from a hot cluster medium ever strips their gas away. Studies of void galaxies from the best mapped voids available show a consistent pattern. Void galaxies tend to be bluer than average, meaning they contain more young, hot, recently formed stars. They tend to have more spiral structure, because the mergers that transform spirals into featureless elliptical galaxies never happen in the void. They tend to have a higher fraction of their mass still in the form of gas available for future star formation. In a dense cluster, a galaxy's active star-forming life might last a few billion years before interactions and environmental effects shut it down. In the void, a galaxy's star-forming life can stretch across the entire current age of the universe and beyond. The quietest environments produce the longest-lived active galaxies. The 60 galaxies inside the Boötes void are likely among the most steadily active star-forming systems in the observable universe. Not the most intense, the most sustained. Each one is a slow, quiet engine running on its own stored fuel, surrounded by darkness, building stars at a pace that will probably continue for billions of years after the stars in most cluster galaxies have long since faded. This matters for thinking about life. If planets form around stars and life can arise on planets, then the timescale available for life's development depends on how long a galaxy stays active. Void galaxies stay active longer. Their stars form over a broader range of times, giving more windows for planetary systems to develop and life to potentially arise. An isolated galaxy inside the Boötes void, forming stars for twice as long as a cluster galaxy, might host civilizations in sequence across an enormous span of time. First wave, then silence, then another wave of star formation and new planetary systems billions of years later. The void, for all its emptiness, might be one of the most hospitable, large-scale environments in the universe for life to persist across deep time. And that raises the most popular, most debated, and most scientifically contentious idea ever associated with the Boötes void. An idea that has spread across the internet and captured millions of imaginations. An idea that the data completely fails to support, but an idea worth examining closely because the reason it fails is as interesting as the idea itself. The story spread quickly. A region of space 330 million light-years across, almost completely empty. Galaxies missing, a structure too large, in early estimates, for natural processes to explain. And sitting at its center, a tube of 60 lonely galaxies arranged in a suspiciously ordered line. For some people, the natural explanation was not gravity, it was intelligence. The idea goes like this. An advanced civilization, ancient beyond imagining, with technology capable of operating at cosmic scales, could theoretically manipulate matter and energy across enormous distances. If such a civilization wanted privacy, raw materials, or isolation, clearing out a region of space the size of the Boötes void would be the ultimate solution. The tube of 60 galaxies is the power source. The emptiness is the boundary they created. The void is a civilization-scale construction project. This idea circulates in online discussions, in science fiction, and in speculative YouTube videos, watched by tens of millions of people. The Boötes void is one of the most popular subjects in amateur cosmology, partly because this idea attaches a human-scale drama to an otherwise abstract cosmic structure. It is worth examining seriously. The Fermi paradox, the observation that an ancient and sufficiently advanced civilization should have had time to spread across the entire galaxy, and yet we detect no clear signs of such a civilization anywhere, is a real and unresolved question in science. The idea that a civilization might deliberately remain hidden, choosing isolation over expansion, is one proposed resolution, but the Boötes void does not fit that picture, and the reasons are precise. The void's properties match the predictions of gravitational structure formation closely. Its size, while extreme, falls within the range produced by simulations of a universe containing dark energy. The tube of 60 galaxies matches what the void merger model predicts for a fossilized filament. The galaxy types inside the void match the properties expected for galaxies that evolved in an isolated, low-density environment. There is no signal in any wavelength from any instrument of energy output, radiation patterns, or structural organization that would distinguish the void from a natural large-scale structure. A civilization capable of rearranging hundreds of millions of light-years of space would presumably leave energy signatures detectable across enormous distances. The processing and manipulation of matter at that scale generates heat, radiation, and organized structure at a level current telescopes could not miss. None of that is observed. The Boötes void is empty because gravity and dark energy made it empty. The same physics that built every galaxy cluster and every filament also built this hole. The void is a natural structure. But here is the genuinely strange part. The natural explanation is arguably more astonishing than the artificial one. A quantum fluctuation smaller than an atom, 13 billion years ago, produced a hole 330 million light-years wide. Physics, without any designer, without any intelligence, carved the largest near-empty region humans have ever found. The universe does not need a civilization to produce its most dramatic structures. It builds them itself, from almost nothing, using only time and gravity and dark energy. And what it will eventually build, trillions of years from now, is something even emptier. Search for an image of the Boötes void, and you will likely find a photograph. It shows a dark circular region on a star field, a black disk surrounded by a faint haze of light. Stars cut off abruptly at the circle's edge. It looks exactly like what people expect a void in space to look like: a hole, a darkness, an absence made visible. The photograph is real, the label is wrong, That image is Barnard 68, a dark molecular cloud roughly 400 light-years from Earth, inside our own Milky Way galaxy. It is a dense knot of cold gas and dust so thick that it absorbs virtually all light from the stars behind it. From our perspective, it looks like a hole in the star field because the dust in front of those stars blocks their light completely. Infrared observations reveal stars behind the cloud, confirming that Barnard 68 is a physical object blocking a view, not an actual absence of stars. Barnard 68 is about half a light-year across. It sits in the constellation Ophiuchus, a completely different part of the sky from Boötes. It has no connection to the Boötes void other than being photographed and repeatedly mislabeled across social media and documentary thumbnails. The Boötes void, by contrast, cannot be captured in a single photograph. It has no boundary visible to a camera. Its edges are defined statistically by the positions of thousands of galaxies at specific distances, not by any surface or edge that reflects or absorbs light. Photons cross the void freely in every direction. Nothing in it blocks starlight. This confusion reveals something important about how humans instinctively imagine cosmic structures. We expect emptiness to look dark. We expect a void to show up as a black region on the sky. But the universe organizes emptiness in a more abstract way. A region can contain almost no galaxies and still be perfectly transparent to light from structures billions of light-years beyond it. The Boötes void is not dark. It is statistically invisible. Its existence is confirmed by the absence of data points, the missing galaxies on a three-dimensional map, not by any direct visual signature. Understanding this distinction matters for understanding what supervoids actually are. They are not physical barriers. They are regions where the cosmic web is almost entirely absent. Space itself fills them. Dark energy fills them. The laws of physics operate identically inside them. A traveler crossing the Boötes void would experience no visual boundary at its edge, no wall, no horizon, just a gradual thinning of visible galaxies over hundreds of millions of light-years until the void's interior, essentially featureless, surrounded them on all sides. And at the void's rim, something extraordinary is happening. The surrounding superclusters, the densest concentrations of galaxies near the void, are themselves extreme structures. The walls around the void are as dramatic as the void itself. Their scale, their mass, and their role in shaping the Boötes void is part of the story that cosmologists are still piecing together. The Boötes void does not exist in isolation. Surrounding it on all sides are some of the largest concentrations of matter in the observable universe. The Shapley supercluster, the Hercules supercluster, the Corona Borealis supercluster, the Ursa Major supercluster. These enormous structures form the walls and filaments bordering the void. They are the drains that matter has been flowing toward for billions of years, and their existence is directly connected to the void's extreme emptiness. The Shapley supercluster is one of the most massive structures in the nearby universe. It contains thousands of galaxies concentrated in a region about 300 million light-years across, comparable in span to the Boötes void, but containing an almost incomprehensible amount more matter. The Shapley supercluster exerts a gravitational pull so large that it measurably attracts the Milky Way, contributing to the motion of our entire galaxy through space. The Hercules supercluster and the Corona Borealis supercluster are similarly massive concentrations. They are nodes in the cosmic web, places where filaments intersect and matter accumulates. Every filament leading away from these structures passes through the cosmic web and connects, eventually, to other superclusters across the observable universe. The Boötes void sits inside a cage of these structures. Matter that might have built galaxies inside the void instead drained along filaments toward the surrounding superclusters over billions of years. The superclusters grew massive, the void grew empty. They are two sides of the same gravitational transaction. This relationship means that the void and its walls are co-evolving. As dark energy continues to accelerate the expansion of space, the walls of the void will eventually stop growing, Dark energy's push will overcome the gravitational pull holding superclusters together on the largest scales. The filaments connecting superclusters will thin and break. The superclusters themselves will gradually dissolve as their outer galaxies drift away. The void, meanwhile, will keep expanding. With nothing inside to slow its growth and dark energy actively pushing its walls outward, the Boötes void will grow larger over cosmic time. In tens of billions of years, the boundary between the void and the surrounding structures will be harder to define because the surrounding structures themselves will be breaking apart. The walls that built the void by draining matter from it are themselves temporary. In the very long run, dark energy will claim them too. But before any of that happens, light from distant galaxies is passing through the void right now, and the path that light takes carries information about the distribution of invisible matter inside and around the void. That information has already changed what scientists think they know about dark matter. There is a way to map matter that produces no light. Dark matter makes up roughly 27% of the total energy content of the universe. It outweighs all visible matter, all the stars and gas and planets and dust, by more than 5 to 1. It surrounds galaxies in enormous invisible halos. It fills the filaments of the cosmic web. It holds galaxy clusters together against the outward pressure of their own motion. But dark matter emits no light. It absorbs no light. It interacts with normal matter only through gravity. No camera, no detector, no instrument built so far has captured dark matter directly. Scientists infer its existence from its gravitational effects, the way galaxies rotate, the way clusters bend light, the way the cosmic web grows. Cosmic voids give scientists a new way to probe dark matter in the least cluttered parts of the universe. The technique is called weak gravitational lensing. When light from a distant galaxy passes near a concentration of matter, that matter's gravity bends the path of the light slightly. The distant galaxy appears to the observer on Earth as very slightly distorted, stretched in a direction perpendicular to the concentration of matter. The amount of stretching tells you how much mass is present, including invisible dark matter. In dense galaxy clusters, this effect is dramatic. A massive cluster can produce multiple images of a single background galaxy, arcing around the cluster in rings or arcs. The lensing is strong and obvious. In voids, the lensing is far subtler. With very little matter present, the bending of light is tiny, but it is measurable, and it gives scientists a way to map the distribution of dark matter in the void's interior and around its edges. Weak lensing surveys of the regions around the Boötes void and similar supervoids reveal that the dark matter distribution closely follows the visible galaxy distribution. Where galaxies cluster along the walls and filaments bordering the void, dark matter concentrates too. Inside the void, dark matter is as depleted as visible matter. The void is empty of dark matter in the same proportion as it is empty of galaxies. This tells scientists something important. Whatever process created the Boötes void, it emptied dark matter and visible matter equally. Gravity treated both the same way, draining both toward the surrounding superclusters in parallel. The void's emptiness is total, not selective. Mapping the dark matter distribution around the Boötes void with increasing precision is one of the goals of current and near-future surveys. Each measurement refines the picture of how dark matter and visible matter co-evolved to produce the cosmic web's current structure, and what the cosmic web looks like on the absolute largest scales. Scales where even supervoids like the Boötes void start to look small, is a picture that becomes stranger the farther out you zoom. Imagine traveling at the speed of light toward the Boötes void. You leave Earth heading in the direction of the constellation Boötes. Around you, the universe looks familiar. Galaxies in every direction, some alone, some in clusters, some strung along filaments, visible even at vast distances. The cosmic web is everywhere. At 100 million light-years out, the surroundings have thinned somewhat. You are entering a less dense region. Galaxies are more spread out. The filaments are fainter, but the universe still looks populated, textured, alive with structure. At 300 million light-years, the thinning accelerates. The filaments around you are becoming threads rather than ropes. Galaxies appear in ones and twos rather than clusters. The surrounding cosmic web is clearly organized, but the nodes are farther apart than they were near Earth. At 500 million light-years, you reach the approaching edge of the Boötes void. There is no wall here, no boundary you cross. Just a continued thinning of galaxies in the direction ahead of you, while the galaxies behind and to the sides remain somewhat more numerous. Over the next tens of millions of light-years, the thinning becomes dramatic. The galaxies ahead are not just fewer, they are nearly absent. You are entering the void's interior. At 600 million light-years from Earth, the void is fully around you. In every direction, the nearest visible galaxy is tens of millions of light-years away. The cosmic web that was visible as a subtle structure outside the void is now invisible. You are inside one of the biggest bubbles in the foam, and the bubble walls are too far away to show structure at normal imaging scales. The tube of 60 galaxies sits roughly here, crossing your path somewhere in the void's middle. You pass near one of them. It is a spiral galaxy, bluer than average, still forming stars quietly in the void's silence. No companion galaxy is visible within tens of millions of light-years. It drifts alone, building stars slowly, unaware of and unaffected by whatever debates are happening among the cosmologists trying to understand the void it lives in. Beyond the galaxy, more emptiness. The tube falls behind you. Ahead, the void continues for another 100 million light-years before the first hints of the superclusters on the far rim appear. At 750 million light-years, the far wall of the void is visible. Galaxies grow more numerous ahead of you again. The filaments appear brighter and denser than anything you saw inside the void. The wall of the Boötes supercluster rises in front of you like a city skyline after a long drive through empty desert. Crossing back into the cosmic web, the universe looks full again. Behind you, the void sits where it always has, invisible except to a redshift survey, enormous, patient, and still growing. Dark energy is pushing its walls outward at this very moment, a millimeter per second of additional expansion per million light-years of void. Tiny by human standards, enormous across hundreds of millions of light-years. The void is the universe in its most honest state, not exceptional, not aberrant. The dominant feature of space, made extreme, and what makes it even more striking is that this is what most of the universe looks like. The interior of the Boötes void is not truly empty. Space is never truly empty anywhere in the universe. Even in the most isolated regions, the quantum vacuum hums with activity. Virtual particle pairs pop in and out of existence constantly. The cosmic microwave background fills every cubic inch of space with ancient photons, 3 of them per cubic centimeter, relics of the Big Bang that have been cooling and thinning for nearly 14 billion years. But in the Boötes void, everything measurable is reduced to a minimum. The intergalactic medium, the thin gas that fills the space between galaxies throughout the cosmic web, is present inside the void at a much lower density than in typical cosmic environments. In filaments and around clusters, this gas reaches temperatures of tens of millions of degrees, heated by the gravitational energy of infalling matter. It glows faintly in X-ray light. Inside the void, there is far less of this hot gas. The temperatures are lower. The X-ray glow is essentially absent. The radiation environment inside the void is also quieter. In dense regions, galaxies and quasars pour intense ultraviolet and X-ray radiation into the surrounding medium. This radiation ionizes and heats the intergalactic gas, keeping it in a particular chemical state. Inside the Boötes void, with far fewer galaxies and no nearby quasars, the radiation field is weaker. The gas inside the void is subject to less ionizing radiation than gas in typical cosmic environments. The magnetic fields that thread the cosmic web, generated by galaxies, active black holes, and the movement of charged gas through filaments, are also substantially weaker inside the void. The void's interior is magnetically quieter than the surrounding cosmic web. None of these differences are dramatic enough to create fundamentally different physics. The laws of nature are identical inside the void to what they are outside it. An atom of hydrogen inside the Boötes void obeys exactly the same quantum mechanics as an atom of hydrogen in the Shapley supercluster. But the environment, the temperature, density, radiation field, and magnetic structure of the space an atom or a galaxy inhabits shapes how it evolves over time. The galaxies inside the Boötes void evolved in a quieter, cooler, less irradiated environment than galaxies in dense filaments. Their gas retained more of its original chemical composition. Their magnetic fields developed differently. Their star formation histories stretched out over longer timescales. The void is quieter in every measurable sense. And that quiet is a record of what the universe looked like before gravity and dark energy concentrated matter into the dense, active structures we call the cosmic web. The void preserves something ancient, a quieter version of the cosmos. And when scientists peer at what that ancient quietness might evolve into, given enough time, the picture that emerges is the most sobering forecast in all of astronomy. Here is the fact that cosmologists sit with and rarely say out loud. 80% of the universe, by volume, is void. The cosmic web, all its filaments and clusters and superclusters and the hundreds of billions of galaxies packed into them, fills the remaining 20%. The universe is structured the way a foam is structured, with thin walls and enormous bubbles, and the bubbles dominate. Most of space is the Boötes void, or something like it. This inverts the intuition that comes from living on a planet, inside a solar system, inside a galaxy. Our experience of the universe is one of density, matter everywhere, stars above us, Earth beneath us. Even the emptiness of interplanetary space is full of particles and radiation by the standards of the intergalactic medium. We are built from the 20% and we see the universe from inside the 20%. From inside the 80%, the universe looks completely different. A galaxy observer inside the Boötes void looks out into darkness. The cosmic web is visible as a faint boundary hundreds of millions of light years away. The nearby universe contains almost nothing. The dominant experience of that observer is emptiness, and yet the void produced them. The same quantum fluctuations that built the filaments and clusters also built the voids. Matter that flowed away from the void's interior moved into the filaments that built the galaxies that contain the stars that eventually produced planets and, potentially, life. The void and the galaxy are linked by the same ancient process. The emptiness is not separate from the structure. It is the structure's other face. There is something else hiding in this picture. The existence of the Boötes void, confirmed by survey after survey, tells us that our intuitions about the universe are systematically biased by where we stand inside it. We assume the universe looks the way it looks from here. We assume our patch is representative. The Boötes void is a reminder that it is not. Our neighborhood is unusual. We live in the 20%. For science, this matters enormously. Measurements made from inside a void would be different from measurements made from inside a filament. Measurements made from the center of a supercluster would be different from both. The universe does not look the same from every vantage point. Accounting for our specific position in the cosmic web is an active area of research, and the Boötes void, as an extreme contrast to our own location, helps calibrate that accounting. For everyone else, the void asks a simpler question. If the universe is mostly empty, and if that emptiness is the normal state of space, what does it mean to call a dense region like ours the universe? We are a small, dense, busy exception inside an overwhelmingly quiet cosmos. The void is not the strange part. We are, and what the void becomes in the far future will make our current cosmic neighborhood look even more exceptional in hindsight. 1 trillion years from now, the Boötes void will still exist. It will be larger, Dark energy is accelerating the expansion of space in every direction. Inside voids, where matter is thin and gravity is weak, this acceleration runs almost unchecked. The Boötes void is growing right now, its walls pushed outward by dark energy at a rate that adds up over cosmic time to something enormous. In 1 billion years, the void will be measurably larger. The 60 galaxies inside it will be farther apart. The surrounding superclusters, still dense by comparison, will have lost some of their outermost galaxies to the general expansion. In 10 billion years, the picture changes more dramatically. Dark energy's push, sustained over that timescale, will have weakened the gravitational bonds holding the outermost galaxies of the surrounding superclusters together. The filaments connecting superclusters will have thinned, some will have broken entirely. The cosmic web, already a foam, will begin to dissolve at its thinnest points. In 100 billion years, the observable universe will look almost unrecognizable from today. The expansion of space, accelerated by dark energy, will have carried most galaxies beyond the cosmological horizon, the distance beyond which the expansion of space exceeds the speed of light and no signal can ever reach us. A civilization in a galaxy at that time will see only a small local group of galaxies around them. Everything else will have receded past the point of contact. The cosmic web will be gone, replaced by isolated islands of matter, each island a gravitationally bound group of galaxies surrounded by an expanding void of space that grows larger every second. In 1 trillion years, each surviving galaxy group will sit alone in an enormous, expanding emptiness. The descendants of the Boötes void and every other void in the universe will have merged into a single universal void, punctuated only by the isolated remnants of galaxy groups too tightly bound to have been pulled apart. Stars will be dying. The smallest, most efficient stars, red dwarfs burning hydrogen at an almost unimaginably slow rate, will still be active, but their numbers will be thinning too. Eventually, even the stars go dark. Black holes remain, and then, over timescales so vast they make the current age of the universe seem like a fraction of a second, even the black holes evaporate through a process called Hawking radiation. What is left is a universe that is almost entirely the Boötes void, cold, dark, expanding, nearly featureless. The void, which began as a quantum fluctuation in the first second of existence, ends as the dominant state of everything. In the very long run, the universe becomes the void. The only question left standing is whether any of our current models are complete enough to predict that future accurately. And the answer to that question depends on whether the Boötes void and structures like it are hiding any remaining surprises. The Boötes void fits the models. That sentence took more than 40 years to become true. In 1981, when Kirshner's team found a hole where thousands of galaxies should have been, no model could explain it. For more than a decade, the void sat in the scientific literature as an uncomfortable outlier, too big, too empty, and too clearly real to explain away. Then, dark energy arrived. Simulations improved. The void merger picture solidified. The tube of 60 galaxies matched the fossilized filament prediction. The integrated Sachs-Wolf measurements confirmed dark energy's signature inside the void. The galaxy properties inside the void matched what isolated evolution in a low-density environment should produce. The Boötes void fits the models. But fitting the models is a complicated achievement. It means the standard framework of cosmology, cold, dark matter plus dark energy plus quantum fluctuations from the Big Bang, can accommodate the Boötes void without breaking. It does not mean the models are complete. The Hubble tension remains unresolved. The nature of dark energy, whether it is a true constant or a field that evolves, remains unknown. The exact mass of the neutrino remains unmeasured. The full census of galaxies inside the Boötes void remains incomplete. The question of whether the Eridanus supervoid is real and connected to the cold spot remains open. The deeper question of why the quantum fluctuations from the Big Bang had exactly the statistical properties they did, and whether those properties were inevitable or contingent, remains unanswered. The void fits the models, but the models have gaps, and those gaps are precisely the territory that the Boötes void is helping to explore. Euclid is mapping thousands of voids right now. Each new void added to the catalogue is a data point. Each data point tightens the constraints on dark energy, neutrino mass, and the overall geometry of spacetime. As the catalogue grows, the constraints grow tighter. If the standard model is correct, the constraints will converge on values consistent with everything else astronomers know. If the standard model has a flaw, the constraints will pull in a direction the model cannot follow. The Boötes void points towards something deeper, a universe that is mostly empty, built from quantum chance, sculpted by invisible forces, and still expanding into an unknown future. The structure that once looked like a mistake in the data is now one of the clearest windows into the largest questions science can ask. And the window stays open. Every new galaxy survey that maps its interior, every microwave telescope that measures its signal in the ancient light, every simulation that tries to reproduce its shape and emptiness adds another line to the answer. The Boötes void has been speaking to astronomers since 1981. The conversation is still going, and the universe, as it turns out, has more to say.